Oye, Inyalora. So, in this video, we're going to take a look at some of the applications in STK that apply to our ISAT C-Series missions. Now, we're going to take a look at least a little bit of both 1C1 and 1C2, but we're going to leave some of the lessons that we introduce with that and some of the analysis that we show in these videos for you to apply in unique ways onto 1C3. So we will not actually be looking at 1C3 in this particular video. There are a few things that we want to talk over. What's new about the C-Series is we're introducing sensors, or as I sometimes call them, scanners, because I grew up watching Star Trek, and so it sounds more fun that way to me. So, in this case, all three of these scenarios are tied together by introducing the idea of sensors, which are more limited in the things that they can do than a regular satellite. But often they represent things like high-powered cameras or radar systems or LiDAR systems. So those are all really cool real-life sensors, but they may have a lot more limitations than just a regular radio or microwave transmission that is normally associated with satellite technology. Okay, so for 1C1, we're taking a look at analyzing air quality around a school district in North America. So one of the things that I want to emphasize on this that I really like about sensors and scanners is they actually, as long as you've got it enabled, show a little cone where you can actually see what the satellite can actually see on the ground. It's like a little spotlight. Sometimes when you're just told, hey, you have these limitations, but you can't physically see it, that's a little bit tougher for me. So on this, I'm going to make this big. We've got that we can see this cone coming down from our satellite. Now technically this is what's called a nadir pointing sensor, and so it always points straight down from the satellite, and by default our satellites are set up that they actually rotate in space where the bottom of the satellite is always pointed towards the Earth. So those are a few things that don't necessarily happen immediately in real life. You have to set them up that way, but they are the standard functions that are programmed in on STK. So unless you go in to change them on STK, if you just add a satellite with a sensor, the sensor, you can switch it from nadir pointing, and you can also change the satellite so it isn't always pointed where the bottom of it is pointed down towards the planet, but those are kind of the defaults. Okay, not that you necessarily fully need to know this, but, well, actually the first part you would. So we've got a satellite here, and if you press the minus sign, it will hide whatever's on the satellite, but I can do the plus, and we can see indented beneath it with a little line to it shows that our OASIS scanner sensor is actually built onto the ISAT satellite, and that's why I'm going to zoom out some. If I press play, we can see that the cone goes with the satellite as it goes, because it's attached to the satellite. Now our target's over in North America. I'm going to pan around to actually getting to that. And then we'll play around with some of the settings on that. But real quick, on OASIS, I'm going to right-click. You don't necessarily need to know this, but it doesn't hurt for you to learn more about how we set these things up. If you go to Properties, now on the satellite, you can go to Properties and change what it's doing. On the sensor, unless you're instructed that you can change it, you probably shouldn't mess with these settings. But I will show you some things so you can see where they're at. We often use a simple conic sensor type, and then that's one that has a cone half angle of some value in degrees. Now that basically says how far from pointing straight down can it see to one side. It can go 10 degrees. So that means that we have 20 degrees total field of view, and it's centered around straight down. Things that you can do on here, we talked about this before briefly. There's pointing type, fixed, or you can actually have a targeted one, or I'm not going to go through all of these, but you have a lot of different options. You can also set it where it is not pointed straight down. You could have it where you could change its elevation and have it pointed a little bit to one side. I'm not going to go into all the details on that. Feel free to play around with them, but if you change something and it's not allowed to change in the scenario, well, you might be getting numbers that no longer give you a correct score. So feel free to play with these to understand more about them, but most likely any of the scenarios, or at least most of the scenarios provided by myself and Stellar, end up having these kind of pre-programmed in for convenience for students. We want you to know these things, but it can be a lot to expect you all to know them. That being said, if you know how to set some of these things up, including the next thing I'm about to go to, the constraints, then those are ones where you might be able to add some constraints in that might make your analysis much easier. Now, you can add those temporarily, but you might need to remove them later in order to actually get the full score. Okay, let's see. Going down, we also have constraints of basic constraints where you can have azimuth, elevation, and most importantly, by my consideration, range, because that's one where you could basically set up that the scanner can only scan so far. Now in this, I haven't actually included any of that, and so this one is our basic scenario where we're just getting used to the sensor itself. I also don't have any sun limitations or constraints in here. We're going to talk about those when we get to 1C2. But we'll get back to that here in a minute. But here are some common places where you'll actually see some constraints where you can put limitations on your sensors. Or you also have this on any of the other objects too. So you could put constraints on the satellite or on the ground station, the facility, or your target, for want of a better term. Okay, so in this case, I'm going to show a little bit of some of the things that I recommend and what I like about the sensor cone. I can bring up ISAT, and we're going to right-click, go over to its properties, and I'm going to not be in full screen because that's going to drive me crazy. I want to be able to see my 3D view. Okay, so first off, I know from experience that this school district is actually much closer to maybe about 35 degrees latitude, and therefore I'm going to set my inclination a little bit higher than the default of just under 30. Let's see, I can take the apogee and perigee a little bit farther out, but I'm going to leave those as is. Right now, my satellite is kind of on the wrong side of the planet for what I want, so I'm going to try and twist my orbit around the planet. Here's where, again, being familiar with the orbital elements might help. Let's see, I probably want to move this maybe about 90 degrees in my RAN. Let's see what that does. Okay, very, very close. Again, this is a good example of if you know what each of these numbers are and how they actually manifest on your 3D track on the globe, then you can actually start to very quickly design an orbit. Now, I don't know if this orbit's ideal, but what I want to do is I want to try and get my target to be underneath that spotlight, my scan ability for Oasis. So I'm getting real close here. I'm going to zoom out just a little bit. Let's see, my satellite is right now not anywhere near my target. I'm getting my orbit near there. It appears to be almost on the other side of the planet. So I don't want to change my orbit, at least in this step. I want to change where my satellite is, and it's about on the wrong side of the planet, so I'm going to apply 180. Oh, looks like I went too far. Maybe I want to do 120 instead. There we go, we're getting much closer. Okay, let's see, maybe 90? That'll probably go too far to the other side. It will. But here's where I can kind of zoom in on it. So let's try 100. That's getting very, very close. Okay, so it's close enough that I'm going to shift my RAN just a little bit more to try and bring it a little bit closer. So let's go maybe 95. Oh, okay, maybe 105. Ah, we're very, very close. Okay, so on this, I could actually adjust a variety of parameters, but I just want to get it where I'm scanning this right now here at the beginning as a starting thing. So since my orbit appears to go pretty much almost right over my target, I'm going to adjust my true anomaly by just a little bit, bring my satellite back by just a smidge. 98, there we go. And with this, I now have it that at the beginning of my scenario, I'm going to double check I'm at the beginning. Ooh, I was not at the beginning. Okay. Let's see. Oh, ISAT's a little bit off, so let me up this just a little bit. I'm going to move my satellite a bit forward. This might be maybe 130. Oh, nope. 110. I promise this will get more interesting. Okay, 115. So I'm starting off with me actually scanning it, and one thing that I'll bring up on this is if I were to, let's see, maybe get this just a little bit off, 104, maybe 103, yeah, and then now if I move this forward maybe to 117, all right. This is something that I wanted to talk about specifically with it. If we watch while I'm going to slow this down, and play, rewind, I've got it where I'm already in my scan area, which isn't necessarily great, and on top of that, right now when I'm scanning it, it's going to cut across basically the edge of my little spotlight. One thing that I might be able to do is try and get it where my spotlight is a little more centered on it. And you saw that I could do that by adjusting a few things. It used to be a little bit more centered, so I could do 105 for my RAN, and then bring this back to 115. And now with this, I've got it where it's mostly at the beginning. I'll probably scan it a little bit longer in this case, and it mostly goes through right through the center. Now, this is one of the things that I wanted to show you with how you can actually go through, and with the visual feedback of this sensor cone, you can go through and apply understanding of what the orbital elements are to try and get the best for an initial setup. But the thing about it is, maximizing what happens at the very beginning might be useful if this were a scenario like, I don't know, series 3, where you only have one day that you're working with. That's going to make a big difference. But this scenario's over a couple week period, which means maximizing the first day might come at the expense of later days. But I wanted to showcase that while we're here. The other thing that I really want to emphasize with the beginning of sensors is how you get your actual numbers. So the most common mistake that I've seen students make is they're used to clicking on the satellite, right-clicking and going to access. They'll go to Edmund OK, our target, click compute, and bring up their access report. And then they'll scroll to the bottom, and then they'll say, we've got 2,300 minutes. We are just killing it. Because according to this, we get scoring. You will earn 1 point for each 6 minutes of scan time. So off the top of my head, we're just under 2,400 minutes. Divide that by 6, and we would end up with 400 points. Wow, that's a really high score. That's also a clue that we're probably doing something wrong. Now, it doesn't matter if the satellite can see this target, because the satellite isn't the thing that's checking air quality. So I'm going to close this. This is the most common problem that students have when they first start working with sensors, keeping track of clicking on the sensor. We want contact between the sensor and the target. So I'm going to click on the sensor and then check its connection with Edmund OK. Now I'm going to bring up my report on that, and we do not end up with 2,300 minutes, and therefore 400 some odd points. Instead, we've got a little over 6 minutes, so we're getting, well, 1 point from this. But then again, I've only done a little bit of playing with the orbit. One of the things that we probably want to do is take this satellite a little bit further out, maybe 1,000 kilometers. Let's see if it yells at me. Yep, it'll yell at me. Same old error. Hello, error, my old friend. Okay. Apply. And then now, zooming out, one of the other things that I want to mention is this. You may have seen it in the background there, but the cone got a little bit bigger because now my satellite's farther out. In fact, let's take that even further out. Let's go out all the way to the maximum that we can, 2,000. And watch when I click apply up here what happens to our scan. Now we've got a much bigger scan area. So, these are things to keep in mind, especially with that angle. The further out you get, the bigger the scan area onto the Earth, or your other target, will be. And now that I've got a bigger scan area, let's go back up to our access report, and we want between Oasis and Edmund OK. Now, because Oasis is on ISAT, you'll actually see ISAT-Oasis. That's normal. I'm going to bring this up, and instead of 6 minutes and 1 point, we are getting 80 minutes, which would be a little over 20 some odd points. It'd be just under maybe 25 points, I think. So here's where you can start going through and working with these things. And by having the visual feedback, if that's something that you can work with, to me, it makes it much easier for me to visualize when I am and am not scanning my target. Okay, give me just a moment. I'm going to check my notes to make certain that I haven't overlooked anything. Okay, no, I think we're doing well. We're going to go to the second scenario in this series, because there are a few things that I actually introduce in that one. Okay, so I'm going to skip past this one. We're going to go to Sentinel's Blind. Now, there are a few things that I want to bring up on Sentinel's Blind. This is one where I made reference to limitations in Fresh Air. I said that the scanner doesn't really work, the sensor doesn't work, when you get a bit above 2,000 kilometers. And so that was one, I think it was 2,000 kilometers. There's a limit in here somewhere where I said that the sensor didn't work very well above that. But I didn't actually put that in as a limitation physically on the sensor. But I could. And that's what I did here instead in Sentinel's Blind. So when it comes to fresh air, it says that the scanner doesn't do as well when it gets to higher values, but if we don't put in a limitation or have some way that you have to account for that, then just say, okay, stick with the regular limitations that we gave you. I gave you a limit on how high up you could put the satellite. I guess that was 3,500 kilometers, and that was the only thing you had to worry about, even though when you're scanning from an angle, it might actually be that you're much farther than 3,500 kilometers from your target. And that's what brings us to Sentinel's Blind. Sentinel's Blind, I set this up as a high-powered camera. Now, cameras use telescopic lenses, among other things, especially if they're going to see very far away. And the way optics works, you can only zoom in so much or zoom out so much before your picture quality starts going to trash. And so in real life, when you have a telescope, you would have one that has a functional range. In this case, we say that, if I'm not mistaken, the sensor that's supposed to represent a telephoto lens, a good camera, has a minimum range of 1,000 kilometers and a maximum range of 2,000 kilometers in order to collect good images of the island. So if you get too close, it's like trying to read a newspaper or a screen and putting it right up against your eye. You can see stuff there, but you can't actually make it out very well, and it's super difficult to work with. The same thing with 2,000 kilometers. Well, you might be able to read what's on your cell phone screen as long as it's in your hand, but if you put it across the room or, say, out across the yard, even with it under its regular settings, you probably wouldn't be able to read it very well. So you have a functional range too. If you're too close, you can't read it comfortably, and if you're too far away, you also can't read it comfortably. It's kind of the same thing with our camera. And so in this one, I told you that we do actually have that straight up physical limitation. Now we've got ISAT, and we can see here my cone actually looks crazy. It's just, I don't actually see the cone, I just see a circle. Well, part of that is, let's take a look. On ISAT, I'm currently at an altitude of 600 kilometers. Well, I said that the sensor doesn't work unless you're at least 1,000 kilometers away. So here's what I'm going to do. I'm going to go to an extreme. I'm going to go to 3,000 kilometers away. Now, it's going to scream at me. Yep. 3,000. Okay. Now we can see the reason why. Okay, so if I come over from the side here, we can see that we've got, it would be a full cone, but the top part of it is actually missing. And we've got kind of a curved bottom on this cone that corresponds to points that are 1,000 kilometers in front of ISAT, or beneath ISAT, I guess. And then the second one is actually 2,000 kilometers below ISAT. So I'm going to look from the side here. Let's go to a big screen. And we can see, here's our satellite, ISAT. And this dark spot where we don't have a cone is all the way out to 1,000 kilometers from the satellite, and we can see that it cuts in. Our cone suddenly appears at 1,000 kilometers out because that's the minimum range for the camera to work. And then it cuts back out again at 2,000 kilometers away. So right now, I'm going to take a guess that I never actually scan the island because I'm too far out. Well, let's find out. I'm going to right-click on OATS, which is our sensor this time. I'm going to click Access, and I'm going to check its access with North Sentinel Island. Reports, and it says no access found because we're way too far up. And here is where those ranges can be important. Okay, now first off, to show that, I can right-click on OATS. OATS is a bigger scanner than the one we saw last time. I'm still using a simple conic on this, and it's still nadir pointing, but it has a cone half angle of 40 degrees. So it actually has a field of view of 80 degrees from one side to the other. I've also included, we mentioned it last time, the constraints, basic. You see that I checked a box here and actually put in that it has a minimum range of 1,000 kilometers and a maximum range of 2,000 kilometers. Now, you could uncheck this and actually remove that. I'm going to click Apply. And now we can see that it removed the far away limit, and now we can scan the entire planet. Well, you may be thinking, well, that's awesome. I'm just going to uncheck that and then get a bunch of points. Well, that's not how we're going to grade it. When we grade it, we're going to definitely put in the real-life limitations. You can't just go, well, I don't like that the camera can't see far away, and I'm just going to say that it can in a real-life mission. But here's where you could adjust these if you were needing to model it to try and see things a little bit differently. So for instance, right now, I get no access on it whatsoever. That doesn't mean that I have a bad orbit. It just means that I'm not getting any feedback because I'm never actually within range. So one thing that I could do is if I'm having trouble finding even the target at all with my satellite, I could temporarily remove the actual limitation and make certain that I can actually see it in principle at some point. Now this number tells me information about when I can actually see the thing, but it's not real information for solving the scenario because it requires me to ignore that the camera can't see that far. But it is something that you can go in and adjust if you're trying to get information that might help you set up for a better solution. So our big problem right now is, one other thing on the constraints. We also said that this is actually a physical camera, and so we're going to take some pictures of this little island, North Sentinel Island. Now the thing about that is, well, it's a regular camera, so we're going to need some lighting. So one of the other limitations that we've got in here, and you can actually see I've included it in the constraints on the satellites. Ooh, my briefing doesn't actually have constraints listed for ISAT. So I will make a note of that and get that. Oh, because the constraints, are on OATS. Never mind, I don't need constraints on that one. I should have constraints none. I may add that and get it re-uploaded. But I've also got constraints on North Sentinel Island that it needs to be in direct sunlight. In other words, it needs to be lit up. So let's take a look at that one. We've now looked at some range limitations. We could also do angle limitations on where it can see. We've also got the sun limitation. There are no sun limitations on the satellite because I don't care if the satellite is in sunlight or not. I care if North Sentinel Island is. Now I bring this up, I can see the actual latitude and longitude, but the big thing that I want to see is the sun setting. And you can see here that I've actually got lighting checked on it, and I've selected direct sunlight because that's what's required for this particular scenario. Here's how I could actually put in a limitation that you have to be in sunlight in order to collect those pictures. Now, I've had a couple of teams reach out to me and say that they were a little confused by that, so I am emphasizing that. And it also says here in the constraints, for convenience, range limitations have been built into OATS and lighting into North Sentinel Island in the provided VDF. Now, make certain that you are clearly thinking out what things need what constraints. My camera is limited by range, so I need to put that range limitation on the sensor, the camera, the OATS sensor. And my target needs to be lit up, so that's the one that needs the lighting constraint. Okay, let me check my notes on here. Let's see. That's pretty much all the main things that we've got on this. One thing that I was going to mention to have you all think about as we begin playing with these scenarios is you might keep in mind that you know that in 24 hours North Sentinel Island will return, or about 24 hours anyway, to about this same spot. So you might think about the actual orbital period, how long it takes for the satellite to orbit in the orbit that you set up. Oh, let me bring the satellite down for just a moment and double check that we actually get some useful times. So in this case, I'm going to bring it down to maybe 1,800 kilometers. That's somewhere in the middle of its functional range. Not in the exact middle, of course, but something that I think might get us some actual contact time. So I'm going to do access, compute, access reports, and we do have some contact time. So with this, we have 56, almost 57 minutes with this by having it where, and you can see here, with our sensor, we actually have a decent scan area. Maybe I should bring it in a little bit closer because then this outer circle will overlap more with the Earth and we have a bigger scan window. But there are some upsides and downsides to that. I'm going to let you all play with that. The last thing that I'll mention is, if I do get a good scan of North Sentinel Island right here, I can think about the time periods that actually show up. I know in approximately 24 hours, it will come back to its initial spot. So if I set up my satellite that it will be back in its initial spot, its good spot, in 24 hours, then I might be able to get really good scan times. Now, the last thing that I'll bring up is a little bit of a mystery for you all to look into. I keep saying about 24 hours. We know that it's pretty much exactly 24 hours, technically, that the Earth takes to rotate once on its axis and go from day to day. I'm going to give you some words to look up. The first one is sidereal. It's spelled out like sidereal, S-I-D-E-R-E-A-L. I always heard it as pronounced as sidereal. And then there's also synodic, which is synodic. That's also called a solar or solar day. So there is a sidereal day, which is how long it takes for the Earth to spin around once with respect to absolute space, which your orbit is oriented in, versus the synodic or the solar day, how long it takes for the sun to reach the same spot in the sky. And those two numbers are not necessarily the same. All right. I think that's all the main things that we wanted to cover in this particular lesson for the C series. Tenye wa cheshkut, and until next time.